Robert Lang is recognized as one of the world's leading masters of the art of origami, with over 700 designs cataloged and diagrammed. He is noted for his great detail and realism, and includes in his repertoire some of the most complex origami designs ever created. His work combines aspects of the Western school of mathematical origami design with the Eastern emphasis upon line and form to yield models that are at once distinctive, elegant, and challenging to fold. Dr. Lang's designs have been shown in exhibitions around the world, including New York, Paris, and Japan. A pioneer in computational origami and the development of formal design algorithms for folding, Dr. Lang lectures widely on origami and its connections to mathematics, science, and technology. He has consulted on applications of origami to engineering problems ranging from airbag design to expandable space telescopes. The title of his presentation today is Origami from Tsuru to Satellites. Welcome, Dr. Lang.
Let's dive in. So from Tsuru to satellites, we're going to make a connection between those two things. Tsuru is the crane, it is the art, satellites are the science, and those are connected by this thing we call origami. So let's start by talking about what origami is. And most people have an idea of origami because you've made flapping birds or blow up bunnies or cootie catchers. And those are all examples of origami. The word's Japanese and it means paper folding. And we use the Japanese word for this art because it goes back in Japan a very long time. This woodcut is from 1797 and it shows these women are holding little strings of birds, and there's a few on the ground here. And if we zoom in, it's this figure, which is the Tsuru, the origami crane, the classical figure of origami that people have been folding since 1797. Or really even longer. This is a samurai sword accessory called a kazuka, and it's decorated with origami cranes. The artist and style suggest it's from around 1600. So for over 400 years or more, people have been folding these sorts of things. This book page from 1734 shows the crane and paper boats that we fold today, and a little man and a cube and so forth. So even by 1734, it was quite well developed. And it's pretty simple though, and it might have stayed simple forever until the 20th century, when this man arrived and took up his art. Akira Yoshizawa is now regarded as the father of modern origami, and he took up his country's craft and created thousands of new figures, and figures of life and beauty. But he did something else that might have been even more important, which was to create a common language for communicating origami. So this system of drawings with dashed lines and arrows and dotted lines that for the first time really conveyed very clearly how to create or how to fold an origami shape. And that led to a new phenomenon because people could teach each other origami in any language using this language. And that enabled growth and sharing, and every person who shared and learned something new added to the art, and then they could share what they had added. And 10 people taught 100, who taught 1,000, and origami spread into a worldwide art form. And it not only spread among people, but it changed the art itself and took it away from the world of blow up bunnies and cootie catchers and simple things to something very different, something like this. This is an origami figure too. It's one uncut sheet of paper. It's one of my designs, a Black Forest cuckoo clock. And yet it is still, just like the crane, one uncut sheet. And if you'll permit me to brag a little bit, from that sheet, we get leaves, we get a deer's head, we get cuckoo, we get pine cones, and we get a clock that is right twice a day. But it lets us create more than just detail. It create life and features, so we can add the horns and ears of an ibex, and create shapes that you might not even think are paper, that look more like maybe they were made out of clay. And figures like this and thousands of others raise a new question of what really changed. And what I think changed in the world of origami, some people get a little upset at, because what I claim is that math came to origami. And some of my friends get a little upset about that because, you know, they say, I'm an artist. How dare you accuse me of using math? But what I mean is that artists and mathematicians and people everywhere on that spectrum began using mathematical ideas. And that was what made all the difference. One of the places it comes in is how we might describe an origami figure by making a plan of the fold. And we can have folds that are shaped like a valley, and we can indicate those with dashed lines, and folds shaped like a mountain indicate with solid lines. We'll call them valley and mountain folds. And this plan up here, this crease pattern, tells me how to fold this origami shape, which is really simple. But every origami shape, no matter how complicated, is still just valleys and mountains. And I'll show what this one turns into a little bit later. So a reasonable question to ask about these crease patterns is, what are the rules and constraints? And you might think that origami, being such an ancient art and have a complex art, that there are really many complex rules, but they're actually quite simple. And for origami that folds flat, they're so simple, we can all learn them. The first is a property called two-colorability that says, if I take a crease pattern and color all the regions so that no two regions of the same color touch, should be doable with just two colors. And if I go to that crease pattern and count the number of mountain and valley lines that come together at a point, the difference between the number of mountains and valleys should be 2. So here you see 1 and 3, and here I see 2 and 4 of the solids. So that, and in all cases, the difference is 2. If I was measuring angles and I number the angles around a circle, I find that all the odd numbered angles, 1, 3, and 5, add up to a straight line, same for all the even numbered angles. And that's true at every single vertex in the interior of the paper. And the last rule is a little more complicated, but it boils down to the fact that the paper can't intersect itself. So if your crease pattern implies a stacking order of the different layers of paper, you could have paper below a fold or above, but it can't be between the layers because it would cut through the fold there. And similarly, 2 folds can be wrapped or stacked, but they can't alternate because they'd have to cut through. And that's it. If you're designing flat origami and you create a crease pattern that satisfies those rules, it's guaranteed to be foldable. And so there's our guidelines for folding. But is that useful? Or is that just, you know, mathematicians playing games and coming up with rules? Well, there's a hierarchy. We can start with the idea of these flat foldability rules, that's math, but then that leads us to an application that tells us how to put together crease patterns, and that lets us generate objects of beauty, create art. But we can use the same rules to create practical functional objects and maybe even make money along the way. And I'm going to show examples of both of those, but I'm going to start with where my heart is in the art. I'm going to start in an area I call textures, which are just patterns of pleats where I fold and unfold in a bunch of vertical lines and then a bunch of horizontal folds. And if that's all I do, I end up with a little pattern of squares, which is pretty boring. I can't do much with it. Well, if I turn it, I can say, and now I have a pattern of diamonds, but that's still pretty boring. But here's what I can do. If I know my rules, I can take a repeating pattern like this. I can combine it with a different crease pattern for a fairly simple design like this fish. But when I put them together, I create art. This koi, folded from a single uncut square of paper, has over 400 scales, takes about 8 hours to fold. If you don't have 8 hours, you can use the same technique just to put the pleats on the back of this turtle. If you're feeling kind of frisky, this rattlesnake has over 1,000 scales. And after I folded this one, I swore I'd never do another 1,000 scale rattlesnake. So the next one had to have 1,500. The same ideas let us create origami on demand. I had a commission where It was a corporate logo. They wanted 5 letters, but there was a week to design and fold it. But using these techniques and repeating patterns and my laws of creases, I could create the crease patterns for the letters. And then here's how it came together. Start with 6 sheets of paper and put the creases into it and start folding them up. Some of you may have figured out what we're talking about, but here it is set up for photography. And indeed, on March 14, 2012, the Google Doodle was folded from origami, and it honored Akira Yoshizawa. These are some of Yoshizawa's butterflies, and you can read the whole story if you Google for Yoshizawa Doodle. So we can create letters, we can create scales, and you might think that's still pretty limiting. But the place where math had the biggest impact in the world of origami was representational design. I want to fold a beetle, and I can describe how to do so with an equation. I take the idea of a beetle, I combine it with a square, and I'll get an origami object. So it's a simple equation, but you know, a lot is buried in these symbols. What do we really mean by plus and equals? And is it even doable? Can you be that specific? Because, you know, this is a beetle, but if we want to get really picky about it, it's a stag beetle that has 6 legs, head, thorax, and abdomen, jaws, 3 points on each jaw plus antenna. And can you be that specific about what you want and then fold it mathematically? And the answer is yes, we can. So how do we do that? And let me go back to that equation and kind of stretch it out, break it up into steps, and also think about how to work backwards from the end. I want to end with an origami beetle. And that means I need a shape of paper that has a flap for every leg and a flap for the antenna and a flap for the jaw. And I'll call this collection of flaps a base. And if I ask what's the minimum amount of information that describes the base, well, I need to know the number of flaps, how long they are, and how they're connected to one another. And I could describe that in words, but an even simpler way would be to draw it as a stick figure, what we call a tree, where each line is a flap, and this shows how they're connected. And we get that to represent the subject. Now, if I want to go forward, going from the subject to the tree, that's an easy thing. Every child can draw stick figures. And if I gave you the base, you could, maybe with a little work, get it to the model by, you know, bending the legs to zigzag and squeezing the antennas to make them skinny and that sort of thing. The hard part would seem to be going from the tree to the base. But that's exactly where math can play a role. So math can get us over the hump in the middle and then create this arc, finish the creative journey. So let's zoom in on that hard part. We have a stick figure, tells us how many flaps we want, how the base should be shaped. And the problem is, how do you make a specified bunch of flaps? And that sounds like a hard problem. And it is a hard problem. But one of the things we often do in sciences is when we're faced with a hard problem, we ask ourselves, what's the simplest version of that problem to start with? And the simplest version of a bunch of flaps is to make one flap. So let's start by doing that. Make a flap. What is a flap? It's a long, skinny bit of paper. And we can do that. You could do that. Because you take a square, and if you just fold it in half until it's skinny, you've got a flap. And you can delineate the length of the flap by making a little bitty fold that says the flap needs to be this long. And when you unfold it, you can see that boundary and realize everything above the fold is flap and everything below is leftover that I don't care. So this little bit of paper is what I needed to make a flap. And if that flap gets skinnier by folding it in half again, as we unfold it, what we find is the boundary gets rounder and rounder. And so in the limit of an infinitely skinny flap, the boundary becomes a quarter circle. And that's the minimum amount of paper you need to make that flap. Well, that's if it came from the corner of the paper, but we can do the same thing to make a flap that comes from the edge of the paper or the middle. And we'd find that the edge takes up a half circle, or the middle takes a full circle. And so no matter where a flap comes from, a circle tells us how much paper we need to make it. And there's another concept we often do in engineering, which is to try to unify separate ideas that really there's always a full circle involved. It just overlaps the corner of the paper, the edge, or the center. So now we know how to make one flap from anywhere. That we've solved the easy problem. We can turn our attention to the hard problem. How do you make a base with many flaps? And now we know the key idea. We just use many circles. We find an arrangement of circles that don't overlap because the paper can only go into one flap at a time. And that arrangement of circles tells us how to make a base that has the right number of flaps to make the thing we're after. Now, it doesn't yet tell us how to make the folds, but you'll notice that the folds, the lines between circle centers, break the base up into polygons. And each of those polygons gives us a little piece of our original stick figure. So to solve the one big problem, we can solve a bunch of little problems. How do we make triangles into three-legged stick figures? And fortunately for us, that solution was already to be found in the world of origami, in patterns we call molecules. You take any triangle and you put folds in from the corners, you make this little three-legged shape whose shadow is a three-legged stick figure. And other patterns gave us four legs. And ultimately, we can combine those, put many of those patterns together to create the crease pattern for the shape that has many, many flaps. And so we have a systematic step-by-step way of designing a crease pattern that is pretty complicated looking, and it might even be intimidating, but it's guaranteed to work. The crease pattern, once you've designed it, it's guaranteed to be foldable into a base. It's guaranteed to have the right number of flaps of the right length in the right place to make the thing we were after. So when we go to fold it, it will work. And this ability, this revolutionized the world of origami. But it takes us to the next question is, what if we had a computer? Could we automate this process? And indeed, we can. Some years ago, I wrote a program that lets you draw the stick figure, and the computer solves the math. It turns out for this particular stick figure, there's 200 equations, but that's child's play for a computer. If you draw it and run the computer, it will pack the circles, draw the molecules, and you'll get a crease pattern. And that crease pattern is guaranteed to have the right number of flaps of the right length in the right place to make the thing we're after. So in this case, the thing we're after is a deer. And indeed, that deer is designed, and with the aid of a computer, still folded by hand. And if we want a different deer, we just change the pattern of circles and we can get different antlers. We could get really long antlers for an elk. Since you folks are up in Minnesota, we can get something especially for you. One of the things we often do in origami is we give away our ideas. We let people know how we did it. The Tree Maker program I wrote is open source, and it's available for download and runs on Mac, Linux, and Windows. And you're free to download it, try it out, and even modify it. And ideas like this led to a lot of new things in the world of origami, but it also led to a competition called the Bug Wars. And the Bug Wars came about because in the 1970s, people thought insects were impossible. But by the 1980s, we realized they were possible. And by the 1990s, it was a battle of the species to one-up each other. So one person would fold a tarantula and then with 8 legs, and the next person would say, well, here's my dragonfly with 6 legs and 4 wings. That's 10 appendages. And the next person would say, yeah, but I'm going to put claws on my beetle. So that's fancier. And the next would say, well, let's do claws and horns. And let's do, well, even more horns. And you actually had origami artists going through entomology journals looking for beetles with more horns. You run out of horns, you can put feathery antenna on your beetle, or you can make something with long, skinny legs like a praying mantis. And if that's not challenging enough, well, we'll do 2 praying mantises still from a single uncut square. And this is, in fact, that crease pattern that I showed you early on. If we want things with lots and lots of legs, we can do centipedes, or centipedes with even more legs. If we want to strive for realism in different ways, well, we could try for a tick, but then let's take it down to life size. But we can use these techniques for much more than just bugs and deer. Representational folds of all kinds. Add feathers and toes to a dancing crane, put the face and feet on an owl, claws and teeth on a grizzly bear, or toes and eyes on a tree frog. Add the shell to a Galapagos tortoise, or spines on a cactus. And this is all one sheet. The back of the paper is red, the front of the paper is green. And it shows that we can make more than one subject from a single sheet of paper. So man playing guitar is one sheet of paper, and the man playing a bass is one sheet of paper. And you might ask if you can do a more complicated instrument than a guitar or a bass, but still make it from a single sheet. And the answer is yes, we can. So this has allowed us to create origami on demand. We can create almost anything. And that enabled origami to blossom in the field of graphics and advertisements and commercials. And as an example, I'm going to show a commercial that I did a few years ago. I'm going to start things running, but I'll tell you before it starts, everything you see except the car is folded paper. その伝説はよく知られている。それは山を支配する。それは注物を支配する。それは風を支配する。それは都市を支配する。それはエンデバと呼ばれている。The 2006 Mitsubishi Endeavor, with a powerful 3.8-liter V6 and available all-wheel drive, a mythic combination of beauty and beast. Mitsubishi, driven to thrill. So a little computer magic to make things move, but even the things that moved were folded paper. Here's a production still from the set. Also shows my collaborator, Linda Tomoko Mihara, who helped design the Victorian houses that you saw. TreeMaker, the program that I wrote, has been joined by many other beautiful software packages for origami. One by Tomohiro Tachi, computer science professor, lets you do for shapes what TreeMaker does for stick figures. Take a shape of a teapot, it gives you this crease pattern, and there's the folded example. And there's software to generate geometric patterns called tessellations. You design it, and then these are folded examples from Alex Bateman, artist. Geometric origami is one of the hottest areas of origami. It includes tessellations that look like geometric patterns, rosettes, sometimes irregular patterns. And many of these are computed only computationally. So here is the crease pattern that when it folds up should look like a woven pattern of stripes. And indeed it does. And then armed with the mathematics of folded paper, we can take things into 3D, include curve folds, thick materials, and other properties needed for real world origami. This is a 3D design by an artist named Chris Palmer that I thought could be generalized. So I wrote a program that's also open source that lets you draw the cross section, and it gives you the fold pattern for a rotationally symmetric shape, which I've used to create pots that are both faceted and sometimes curved. Curved folding was long considered to be the holy grail of origami. So of course I had to do a holy grail. And in this one I call lava lamp, it's just purely abstract. And this geometric field of origami has roots not so much in the Japanese art, but the world of computer science. Ron Resch was a computer scientist back in the 1960s who patented various folding patterns. Here's Ron and some of his most famous work. But he created roof-like shapes, spirals, curved folds. Another mathematician was David Huffman, who developed the mathematics of a lot of curved folding. This is one of Huffman's patterns. If you hold the edges and pull, it sort of spirals and unwinds in a cool way. And when you look at that, you think, well, that's cool, but that could also be useful. And origami has turned out to have many applications in the real world: space, automotive, medicine, and more. This is one application, a pretty simple one. It's a map of Venice that it unfolds in a single motion. Grab opposite corners and pull, and it unfolds. It was designed by an engineer named Koryo Miura, and he wasn't trying to build a better map. He was in the Japanese space program, and he realized this zigzag pattern, now called the Miura-Ori pattern, has the property of unfolding in a way that makes it suitable for things like solar arrays. And indeed, a solar array based on it flew in a Japanese mission in 1995. Solar sails are another thing that deploys. This is a Japanese mission that photographed as it deployed, and you can see the fold lines as it is unfolding. And in the US this year, we will launch the James Webb Space Telescope, which is a telescope that has two folds in it. The whole telescope folds down into this small bundle because it needs to be small for the journey to fit in a rocket, but big and flat at the destination, in this case, outer space. Back around 2000, Lawrence Livermore had the idea of a telescope in space that should scale to 100 meters diameter, football field sized telescope. In this case, they needed to fold the lens. Now, how do you fold a glass lens? You cut it up and you put in Fleischer hinges in the panels. But what fold pattern do you use? They, being good engineers, said, let's look into the world of origami and see if there are things we can adapt. So I got involved with them. We designed some spirally patterns like that Fleischer I showed a little bit ago, created a fold pattern that folds down into a cylinder and scales for larger and larger patterns and larger cylinders, built some mechanical prototypes that folded, and so that ended up in their first generation telescope shown here on its test range in Livermore, California. Current project at JPL is a space-based telescope called Starshade. The idea is to create this unfolding shape that blocks the light from a star so you can see the nearby planet. It too needs to deploy and unfold, and it can't have any cuts because you need to, in the central ring, you need to perfectly block the light from the star. And so what do? We use origami. So this is the origami Fleischer pattern being developed for this star shade. It folds up into a neat little cylinder. And here's a video of one of the larger prototypes being tested. And all of these strings that you see are for what's called gravity offloading to simulate the unfolding in 0G as it unfolds. So we're using unfolding as a method of deployment here. And you can unfold to deploy many things. At Surrey Space Center in the UK, they're making booms that are folded up, packed into a little cylinder, and then when you puff air into them, it expands into a long boom. Small for the journey, and then larger at the destination, has terrestrial applications. This kayak, developed by Oru Kayak, unfolds, and then you actually refold it into the kayak. So you can carry it to the water's edge, then fold it into the kayak. Back in 2009, an artist named James Hart designed this twist bottle that, when it's not in use, folds down into a very small package. And this same fold pattern has been found to be useful in many places, including a microwave antenna developed at the Florida International University, and fashion designs by a couple of fashion designers, Adrian Sack and Lin Wen. My colleagues at Brigham Young University have used origami to make Bundt cake pans. They served Bundt cake at the scientific meeting where they presented the pattern. Of course, if you're going to eat it, you need utensils, and there are origami utensils that fold up. These patterns show up over and over. They're almost timeless. In the sleeve of the Mona Lisa, we can see an origami pattern. This is not just wrinkles. It was an intentional fashion design pattern at that time. But we see this same folded pattern in use in a drink can designed by Corio Miura. By impressing folds into the can, it makes it a little stronger and therefore uses a little bit less aluminum. Sometimes we can use origami just for decorative purposes. These are lamps designed by Yuri and Katrine Shumakov that use origami in the diffuser. We can also use curved folding to make things like lamps. Here's a crease pattern I designed called Elliptic Infinity. That when I saw it, it kind of reminded me of a lamp. And I thought, well, maybe we can make it into a lamp. So, well, let's figure out how to make it from a material other than paper, which we do by breaking it up into discrete folds, and then origami can also be used for structural materials. A company in research institute in Germany uses origami patterns similar to the Miura-Ori to make structural panels, folded either composite materials or carbon fibers shown here. And these are strong enough to hold the weight of a car. They're being pursued for use in aircraft frames to make super light but super strong panels for aircraft. Now, these materials are no longer paper. It's glass fiber, carbon fiber. And in many cases, they're thicker than paper. So we need new mathematics to tell us how to design and model things that aren't paper. So how to take an origami paper model and modify it so it will work with thick materials. My collaborators at Brigham Young University have developed both mathematical theory and physical mechanisms demonstrating the techniques to make things from thick materials. And when we try to fold them, they end up having the same kinematics as if they were made from paper, but they can be made from very thick materials indeed. And that brings us to a design paradigm whereby we can start with a paper model, such as this model, for a bulletproof barrier for law enforcement, then move to a thick origami version, like this video, that deploys in the same way as the paper, but is now thick material. And then we can go to the real material, which in this case is multi-layer Kevlar. It can be handled by one person, but provides shelter. Question is, does it stop bullets? And there's really only one way to know.
Today's objective was to see if it worked, if it actually stops bullets.
My first thought was...
His first thought, and mine as well, was that it might not, but it stopped every bullet they fired, every handgun bullet they fired at it, all the way up to Colt 45. Now, we can use origami to prevent making holes in people, but we can also use it when we want to do that intentionally, which happens in the world of medicine. There's a heart implant developed by a company called Paracore Medical. It's injected between the ribs. It's a sheet that wraps around the heart. And so this sheet-like thing needs to be made small enough to fit between the ribs. Once again, small for the journey, larger at the destination. And origami gives us the way of folding it into this tube. A stent developed by Zhong Yu at Oxford University and Kaori Kurabayashi is the same thing. It needs to be small to be threaded through the blood vessel. Then when it gets into place, it opens out into, in this case, a cylindrical sheet, the tube that holds open the blood vessel. And an artificial liver cell being developed at Northeastern University also was based on origami to replicate the sheet-like pattern in true liver lobules using origami patterns. And this is an example of how to fold some of these materials, where we sandwich the artificial substrate between paper, fold it, take away the paper, and then we're left with the substrate, which is this little zigzag piece. As you can see, this is really tiny. And when you get to tiny things, you run into a new problem of how do you fold tiny things? And well, one solution is you assign it to a grad student and tell the grad student to fold it. But even grad students have their limits. So the best thing to do is to find materials that will fold themselves, as this material, developed and explored by Michael Dickey at North Carolina State, does when exposed to light. And they've actually made things that fold with two different colors. Red folds the fold on the left, green folds the fold on the right. But maybe you're in an environment where you can't use colored light because it's opaque, but you could use magnetic fields. And so a material being developed by Mary Freckler at Penn State folds in response to an oscillating magnetic field. My colleagues at the University University of Massachusetts Amherst are developing materials that fold themselves in response to temperature in an aqueous or water environment. You put patterns of gels, and then when you vary the temperature, the gel swells, induces a fold. So we can take an origami pattern, use photolithography to define the folds, and then when we raise the temperature, it unfolds, and when we then lower the temperature, it will refold itself. And so this makes a reversible little robot. And this is what we think the world's smallest origami flapping bird. It's about 400 microns in size. So basically the size of the cross-section of about 10 human hairs. And then this raises the question, how small can we go? At what scales does folding happen? The very smallest scales. Because proteins fold. We see these cartoons with protein that look like strips of folded paper. And indeed, at the atomic level, although these are cartoons, at the atomic level, atoms behave like folded paper. So if we understand the fundamental laws of folding of paper, then we can apply those to help understand the fundamental laws of how to design the protein molecule. And at the very smallest scales, DNA molecules can be made to fold. Back in about 15 years ago, Paul Rothman at Caltech developed techniques to fold DNA into molecules. And you might say, why would you ever make DNA fold into a smiley face and it's just to have a cool photo? But there are real practical applications of this. In this case, this is work done at Ohio State where they're using DNA origami to fold DNA into a wrapper around an anti-cancer drug. The cancer cells swallow the origami, they unfold it, releases the drug, and it kills them. Even the ideas of origami have use. The patterns of those molecules that I mentioned earlier on turned out to be useful in simulating airbags. And so by using origami to tell us where to make the folds, we can use that to design better and safer airbags. At the highest dimensions, at the highest size scales, we find origami occurring even in higher dimensions. Simulations of dark matter turn out to show that the dark matter folds in sheets like origami, but folding space itself. And although this is a cartoon representation, people now doing simulations of dark matter formulation show actually the formulation of these sheets and these little triangular twist patterns that we saw originally in the world of artistic origami. You can find many more examples of applications of origami, some on my website, some in a wonderful documentary called Between the Folds, and a PBS Nova episode called The Origami Revolution, where you'll see more about the star shade. And there will continue to be more developments in this field as we go forward. Sometimes they're mundane. This one, called Trailer Tail, has just a few folds in it, but it cuts wind resistance and so increases gas mileage. And if you multiply the effects by the number of cars on the road, it could make a pretty substantial difference. And some of the applications of origami are out of this world. One NASA program needs a 25-meter solar array for extrasolar, for outer planetary missions. And once again, they turned to origami to be able to collapse the array and then unfold it in its deployed state. The thing I'd like to leave you with, though, is an idea that many of these designs that have showed up in NASA and medicine and satellites and so forth had their roots in the world of pure origami or the world of pure math. And people laid the groundwork because they were pursuing something, not because they thought it would be useful, but because it was interesting, because it was fun. And so I would encourage all of you to pursue your curiosity, to follow your curiosity, to investigate areas that are interesting, investigate areas that are fun, because those areas you discover, much like the world of origami, might discover a new world or even save a life. And thanks for your attention.
Thank you, Dr. Lang. And now let's turn to some questions from our audience. First of all, could you share again that link to the open source, your tree maker program? Someone was asking if you could post that again.
Yes, probably the easiest way to find it is just Google the word tree maker, but let me go see if I can find it back in my slides that I can pop it up real quick. Scrolling, 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 and there it is. So let's see, let me share my screen. So there it is. So go to my website, langorigami.com, and treemaker.htm, or just Google the word tree maker, and that'll take you directly to it.
Excellent, excellent. Another question, does the accuracy of the fold matter for your designs? That is, oftentimes when one folds a paper airplane, it may end up a bit crooked. So accuracy of folding.
Accuracy is really important, especially in complex folds, because one of the things we see is that errors not only accumulate, they amplify over the course of a fold. So even if you're making small errors at the beginning, their effects grow larger and larger as you work through the folding sequence. So yeah, accuracy is very important and most important in the most complex folds.
In the case of the origami stent or space telescope baffle, is it difficult to collapse them?
It depends on the specific fold pattern, but one of the things we strive for in designing fold patterns for these are patterns that have relatively few degrees of freedom, meaning all the folds tend to move together at once. So in the case of, for example, that star shade, the occulter, even though it has many, many folds in it, you only need to push it in a few places to get it all to fold together. You don't actually have to put your fingers on every single fold around the pattern.
Another question, what does it mean for dark matter to fold, and what would impel it to do so?
The force that impels it is gravity. That is, to our knowledge, the only force we know that acts on dark matter. So it basically attracts itself. But what they find is that that when it evolves under the laws of gravity, it organizes itself into sheets, and then those sheets come together. Where the sheets come together, the way the individual particles move is organizes into things that resemble folded sheets. So it's really the fundamental math that is telling it, the fundamental laws of gravity, that's telling it to behave in a way that is analogous to origami patterns.
Someone has asked here, what fold are you most proud of? And what practical applications are on the horizon that you are watching that haven't yet been solved?
The folds I'm most proud of is usually my latest artistic fold. And so the one that I'm actually most proud of right now is a bird, which may not sound very complicated, but I really like it. And it's on the front page of my website, so you can click over there if you want to actually see it. As for things I'm watching on the horizon, I'm consulting right now on a device. I'll just say it's a cancer treatment. And I'm really eager to see that particular treatment out in the world. That'll end up using some of the consulting and analysis and designing that I've been doing. And I'm sorry, I can't say what it is at this point.
We'll be watching for that.
Yep.
Could you talk a bit about your work with the napkin problem?
Oh yeah, so the napkin problem, the napkin problem came to life as a posting on a mathematical mailing list where the conjecture is, if you take a square napkin, there's no way to fold it so that into a flat shape so that the perimeter of the flat shape is larger than that of the original square. So if for example, I take a little bitty square here, if I fold that corner down, I've trimmed off that corner, the perimeter got smaller. If I fold the corner back out, I've made it larger, but it's still smaller than the original square. And the conjecture or the challenge was to prove that's always the case. And when I saw that, I knew it wasn't the case because I had already designed an origami model that would, a sea urchin, that if you squashed it, would be a counterexample. It had 25 spines and made a little star shape. And if you counted the perimeter going in and out around all of the spines, it would have been larger than that of the original square. And so I wrote up, so I knew that it was not true. So then I wrote up a little bit more mathematical counterexample for it. And I posted it, I think, on a mailing list. And eventually on my website, somewhere there's an article about this problem. And there have been a few articles since where people have sort of addressed the mathematics in different ways, but it all boils down to the basic idea that in addition to creating perimeter from the raw edge, you can also create things that poke out that come from the middle of the paper. and that's how you get longer, how, how you get greater perimeter than the original square.
How does software like TreeMaker encode the order of folds?
It doesn't necessarily, software doesn't necessarily, TreeMaker actually does, well, let's see, there's two types of order. There is stacking order, which TreeMaker calculates, meaning when all the layers are stacked up, what's on the bottom, what's next, all the way up to what's on top. And then there's a separate question of, if you make the folds, in what chronological sequence do you make them? And generally, the software doesn't address that, because in many cases, there is no way to break it down into a step-by-step sequence. They all have to happen at once. In the origami world, there's now a term for that. We call it a collapse, which just means a whole bunch of, the paper collapses, a whole bunch of folds happen all at one time. And one of the big sort of surprising discoveries of the mathematical era was that very often there is no sequential order, that the mathematically designed patterns usually can only be folded using a giant collapse rather than step-by-step process.
Are there examples of folding in insects, earwig wings, etc., that have influenced engineering ventures? In other words, biomimicry.
There's probably been some. I don't know of specific connections. There are definitely people studying. Well, yeah, I'd say, I guess there are, because I realized there are people studying insect wings in particular, earwigs being one of the more famous ones because it has the largest packing ratio. The folded up wings are smaller compared to the unfolded wing than almost any other creature. But there are some insect wings that when they unfold, they snap open. So they don't just smoothly unfold, but they actually pop open. And those popping mechanisms are being studied to be incorporated into mechanical mechanisms for things that might need to open quickly, or open and then stay in a stable open state.
How will the art of actual human beings designing new, intricate, beautiful origami objects be preserved and celebrated now that computers can design anything?
Well, computers are tools, and they can only do what a human mind tells them to do. So as tools, they only augment our own capabilities. And so if we look to other art forms, like to take painting, for example, the tools that were developed are things like brushes and pigments, and mathematical tools like how to do perspective. And each of the development of these tools allowed artists to create a larger range of vision. But it's the artists themselves who select what tools they use, how they're going to use them, whether or not to use them, and what the artistic effect is that they're after. And so all the computers and laser scribers and all these other origami paraphernalia do in the world of art is they give the artist a broader palette of things to choose from.
Are any of the NASA space program applications reusable? Like, could they be refolded during a mission and transported to a different location or back to Earth for further use?
As far as I know, all of the folded shapes that are being developed for NASA are intended to stay unfolded. You know, if we send things to outer planetary missions that take years and years to get there, we'll never get those spacecraft back to Earth. There are, however, some, I think probably some examples of things like solar arrays that might, that might collapse down if something is going to be repositioned and then expand out. But for the most part, in space, once it's up there, you want it to stay open.
What was the most surprising application of origami in your experience?
Well, it would be one of the early ones, because as time has gone on, nothing surprises me, because I mean, even if I've never seen it before, I think, well, of course, origami ought to. But early on, the airbag simulation problem was kind of a surprise. The fact that the molecules, and specifically the universal molecule algorithm designed to create insect legs, turned out to be the tool to be used for the collapsing of an airbag in simulation was a surprise, and a very pleasant one, because it then did give an application to this thing that was developed purely for artistic purposes originally.
Who are 2 or 3 people that have influenced you, and who are some of the up and coming origamists?
The older I get, the more I recognize the number of people who influenced me. But early on, probably the most strongest was Neil Elias, who was an American origami artist. In my teenage years, Neil invented a lot of the techniques of box pleating as a design methodology in the 1970s. He shared through postal mails some of his designs and ideas with me, and that had a huge impact both in the techniques of design, but also in my overall attitude, recognizing how much I learned from what he shared with me made it important for me throughout my life to share and hopefully play that same role to someone else. So he was a big influence. Yoshizawa, the great Yoshizawa, was a huge influence. Also, John Montrol, American designers, just a little bit older than me, but incredibly inventive, and he got my mind going in lots of ways for design. For the young up-and-comers, there are now many more. I'll just name one who comes to mind because I love his work. Kota Imai is a Japanese folder, specializes in insects, and designs the insects that I wish I designed myself. They're just so beautiful and perfect in their design, both mathematically and naturally in their visual appearance.
What designs do you find to be the most mathematically complex, and are there any modern equivalent to the bug wars?
Yeah, definitely. Mathematically, the most complex are now probably some of the human and anime figures. There's a bunch of young folders who create either semi-mythological monsters from anime and human figures from anime. I think they are strongly inspired by the human figures of Eric Joisel, who is a French folder, but they're now very, very intricately detailed. Oh, and also Takashi Hojo, Japanese folder, who did several samurai characters. And so these things are tremendously complex and intricate, take tens of hours to fold, have thousands of creases in them. And there seems to be that same spirit of kind of friendly competition among these types of characters and among those folders that I saw back in the 90s during the bug wars.
Totally fascinating. Thank you for sharing with us. Do you have a final comment you could leave with our audience today?
I'll repeat just in my final message of that I encourage people to follow their curiosity, and share my favorite quote by Louis Pasteur is, "Chance favors the prepared mind. You can't control the opportunities that come to you, but what you can do is prepare your mind to capitalize, to recognize those opportunities and act on them. And you can do that by learning a lot about a lot of different areas. and not worrying whether it's eventually going to be relevant. But if you know a lot, some of it will.
Thank you again, Dr. Lang, and thank all of you for joining us today. And I encourage you to tune in again next week when comedian and performance artist Christina Wong discusses reality television, political theater, and social change. Until then, be well and be kind.